Oh no. Someone just realized you can't use vectors. Oh no. Oh dear. Okay, well, sorry about that, Brad. Welcome again to another episode of... It feels like I'm on a really lame TV show. Intrigued and concerned. Another episode of 341. Today we're doing one of my favorite data structures. So I hyped up trees. We're done trees! Yeah! Woo! We did that! How long did that take? I told you it'd be like a month. There was a lot less board game playing because we weren't in class. How sad. This is actually another topic I want to make a board game for, but I haven't gotten myself sorted to do that yet. Anyway, in the meantime, we still have a fun hands-on activity. Also, those of you who are concerned about the delay is only about 5 seconds now. My big dumb brain missed the fact that there's a stream latency setting, and so now the stream is much less delayed. I have noticed that as a result of changing that, occasionally the stream will just drop like 5 to 10 seconds. So, yeah. Is the AVL visualization used in class an accurate way of checking our balanced trees? No! You are not doing AVL trees. These are a different kind of balancing mechanism, so you cannot use the AVL tree to check your work. So, yeah. I might talk about the project a little bit more at the end, but at this point, it's due Friday, and I want to keep kind of trucking through the class material, but I might do another brief explanation of some common questions I've heard from everybody. So yeah. Alright, hold on, let me get my questionometer up here so I can see the questions. Okay. All right, here we go. When was that exam due date? It's a while, I think. It's in the course website. Let's go have a little gander at the course website. Let's have a look here. Is there a section page? Let's go down. It looks like the second midterm is 422. The review's on 420. When we submit the project, should we also submit any text files we made to test? I don't know. Let's look at the project description. Projects. I would assume yes for this project, because your scan test is probably going to want to load in a text file. So do put anything that your scan test requires. Okay. So if your scan test requires some TXT files, pop them in there. All right, cool. All right, let's get to the lecture. I'm excited. Hash tables are amazing. So good. There's a really good reason for picking a baby otter for the hash table lecture. So way back when hash tables were first invented, I'm just kidding. It's just a really cute, that's a really cute otter. Like, isn't that cute? This is the point in the semester where we just need cute animals to happen, right? So that's a cute baby otter. Oh gosh! Project 3 is not due Saturday. I forgot to change these. Project 3 is due Friday. You see, we're still on pace with previous semesters. And that's pretty much the story. Exam is the 22nd. Exam 2 is tentatively, I might move it up the 22nd. It'll be a take-home exam. I'm not doing all that lockdown browser stuff, so it'll be a... Let me just check the live stream. it's not updating. Update, you fiend. It just, and okay. Cool. All right. Exam is tentatively the 22nd. I might move it up to the 20th because, like, a review class might not be as constructive if we can't do it in person. I might just release a review video. That will make the second exam easier because there'll be less content on it if I move it up. So if you have any incredibly strong opinions about the exam, let me know. So what's the fastest? We've been talking about the performance of data structures. So let's get down to business here. Some data structures allow us to create and retrieve in constant time, and some offer both. What are they? So I should have to wait less time now. I'm going to do this so I can see the delay. Should have to wait less time now to see your questions or your responses pop up. But pop in chat, what data structures thus far allow us to create and retrieve in constant time? All right, there's the delay. So that was probably about 10 seconds. What are they? There's 2. 3, technically. There is a 341 Discord, correct. All right. Oh, I thought Tenny was saying she had a question, but queues. Yeah, stacks, queues, and decks, or DQs or whatever, they both offer insertion and removal in constant time. What limitations do they have? Well, you can only insert or remove, like, a particular item. So if you have 10,000 things in your queue, as you're well aware with the office hours queue, you can only DQ the thing at the front. Yeah, stacks as well. So that's a limitation we have. How fast, if we want to figure out if someone's in a queue, how long does that take? Well, what do we have to do? We would either have to DQ everybody and then re-enqueue them until we find the one that we're looking for, or if we have access to the internals of the data structure, we'd have to scan the inside of the data structure. In either case, it would take us linear time to find something. What if we had a data structure that let us get at everything in constant time? So today we're going to learn about that. We're going to learn about, yeah, Kevin's got it. It's N. Today we're going to learn about hash tables, and they're amazing. When in doubt, hash table. And if you can't use a hash table, balanced binary search tree is sort of the motto of this class. It's sort of the takeaway. There's some more subtleties regarding priority queues, disjoint sets, Bloom filters, all this other stuff. But in general, most of the problems you're going to get, like, have to solve. You're either going to use a hash table because they are wildly performant, or you're going to use a balanced binary search tree because they are also very performant. So hash tables implement the map ADT. So hash tables are a key value store. Before we implemented maps, before we implemented maps with balanced binary search trees, right? So when we implement a map with a balanced binary search tree, like you're doing in Project 3, you have a key, which is the which is sort of like the key is how you access a value. It's like the number you get at the hat check place. And then there's a value that gets associated with that key. So right now in your project, you have an integer that represents the weight of a particular value in a scrambled image. And then you have the value, which is the actual character, pixel character in that pixel of the scrambled image. So that's a key value store using a balanced binary search tree. Is the office hours one is the 341 one, yeah. And there's a standard CS one. So if you're only in 341, then the only ones, there's also a generic UMBC one, but you're not going to be, I mean, there's stuff there, definitely, but You're not really missing a third one. So how fast is insert in a balanced binary search tree? Well, your worst case is you have to go all the way down to basically insert a leaf at a new depth. And since the depth of the tree, since the height of the tree grows logarithmically with the size, then the performance of a balanced binary search tree for insert and find are logarithmic. Logarithmic is still really fast. Like if you have 1 million things in your tree, you're going to be doing, what, 12 hops to find something? It's a lot better than a linear store where you'd be doing 1 million hops in the worst case, which is bad, right? So hash tables are even better than logarithmic. They're actually just amazing. So how much better? They do everything in constant time. Constant time. Everything. Insert, remove, constant time. It's so exciting. They're so good. But, like, there's no such thing as a free lunch, right? Kinda. Right? There's always some problem, right? With stacks and queues and decks, you had to deal with the fact that you, like, couldn't get all the data at once. So what is the evil, what is the weird problem we're going to have with hash tables? Like, why wouldn't we always just use hash tables? I mean, the answer is most of the time we do, but there are certain circumstances. There is a bit of a price to pay for using a hash table. And then the second thing is, what do we use, right? Thus far, we've used arrays and linked structures, right? So for priority queues, we had an array implementation in the min heap, and then we had a linked implementation in the leftist heap. All of our balanced binary search trees were linked structures. When we went over queues and stacks, we had array implementations of them and linked list implementations of them. So what do we use here? Do we use an array? Do we use a linked structure? Is our hash table so incredible that there's like a new thing that we use? Is there a new thing? No, there isn't a new thing. We're going to use arrays. We're just going to use arrays again. There's nothing new. There's nothing new under the sun. It's all arrays or linked structures. But we're going to use them in a fairly clever way. What we're going to do is we're going to put our key value pairs into an array, okay? And for each key value, for a key value pair, we're going to have a magical function. It's a magical function. And that magical function is going to, if we give it a key, it will give us back an array index into that array. Okay? So this magical function, you give it the key gives you the spot in the array to store things. And it will always give you, if you give it the same key, it will always give you the same value. That's a feature of this mystical magical function. So if I have an array of size 10, and I give it the key blunderbuss, it will give me 5. Every time I give it blunderbuss, it will give me 5, which means that if I'm looking for blunderbuss, it'll give me 5, and I look in array index 5. And if I'm looking to insert it, I know where to put it. I need to put it in array index 5. It's so mathematical. Is there recursion involved? No! There's not even recursion involved. Hash tables are actually extremely memory efficient. So the function, however, that we give blunderbuss to, or whatever we give our key to, this mystical magical thing, which we're going to call a hash function, must run in constant time. If it doesn't run in constant time, then we lose our constant time guarantee. So we're going to say it's a constant time function that you give it some value and some key value, and it'll pop out an array index for you. All right, so today, some of you have already wondered about the title of today's stream or lecture, which is kitty hashing. Why didn't we just learn this first? That is the best reaction, by the way. Why didn't we just learn this first? Well, later we're going to talk about the dark side of hash tables and why you don't use them everywhere. Well, actually, okay, I'll just spoiler alert. The reason you can't use hash tables everywhere is because they deliberately unsort things. So if you want to get things back out in key order, you're sunk. You're back to doing a sort. So if you care about the fact that your keys stay in some kind of sorted order, then you don't want to use a hash table. It's a bad idea. But I love that. Why didn't we just learn this first? We didn't, and the other reason we didn't learn this first is because they are still fairly complicated, and they'll be the topic of your project 4. They're not as bad as trees, though. After project 3, you're mostly over the hump in terms of difficulty. It should be. You're not going to be in free fall. It's still going to be difficult, but it should be easier. I haven't seen project 4 yet, so no guarantees. And there's only 4 projects this semester. All right. Are they hard to use? No. I mean, if you make any data structure, if you write it well, you don't need to. Okay, so here's how our cat hashing is going to work. We're going to use a pre-made hash function. This came from a cat expert, me, and each picture is going to have a set of kitties in it. Okay, so we're going to look at a bunch of kitty pictures. Again, we're having a hard time. It's a rough semester to be in 341. It's a rough semester to be a human being. So we're going to hash some kitties today. So we're going to look at pictures of kitties. Each picture will have a set of kitties. We're going to give the kitties a score. And now I need to make a point here. The kitty score here is a sorting score. It's a metric. It does not speak to the cuteness of the kitty, the quality of the kitty, the happiness of the kitty. We're just using these scores to find the kitty a nice home. So don't worry, we're not going to be judgy about kitties today. So what we're going to do is we're going to have a home for 10 kitties. So I have a home I have the homes for 10 kitties here. And it's going to be an array of size 10. So we have index 0 through 9. Hash brown table. That's, I think, sort of where hashing comes from. Why you got to build this up to some almighty data structure? It is a really good data structure. Python dictionaries have hash tables underneath of them. And dictionaries are incredibly useful in Python. In fact, there are whole databases called NoSQL databases that are giant hash tables. Most caching systems are hash tables. The internet, like, I cannot hype hash tables enough to the point where I want to be able to say that everything you can touch in the world is really a hash table. It's not quite that much, but hash tables are everywhere. All right, so each kitty gets a score. So we're going to get a kitty score, then we're going to mod it by 10. So we're going to have our hash function is going to be total kitty score, TKS. Because come on, guys. Come on, it's TKS. Get with it. All right? I'm not even going to put that on the exam because you should know what TKS is. All right, so we're going to have total kitty score, and then we're going to mod that by 10. All right, so here we go. But first, let's go find some kitties, guys. Let's go find some kitties. Let's go find them. Why not just teach 341 with Python? I actually think I would rather use C++ for a lot of data structures programming. Pointers are a pain, but like they're more explicit and honest. Python, it's like weird. Put it on the exam though. No. As a student, I always hated when there was stuff on the exam that you had to be in lecture for that had nothing to do with the class. All right, so now we're going to go into this document. It's in the lecture slides. You probably saw it early in the semester and you're like, what the hell is this? It's titled A Document Filled with Kitten Pictures with Values. For this, I'm going to make myself larger. So you can see the kitty hashing happening. And we're going to make some adjustment, maybe. And then I should have done a custom setup for kitty hashing. All right, this should be good. I think. Okay. So look, we're at the bleeding edge of instructional technology. I don't want honesty. Why are we learning hashing on the 20th? That's a good point. So here comes our array. I might need to...
I'm sure you know nothing about that.
I don't know anything about hashing on the 20th. Oh, wait. Does this make... No. This makes sense. Right? Yeah, because 0 is on the right. So we have 0, 1, 2, 3... 4, 5, 6, 7, 8, 9. Oh, and then my soldier's in the way. Okay. All right. Okay. So here's our array. This is my extremely high-tech array visualization, brought to you by like some sort of special mindscape. This is like imagination in action. So here we have all the indices from 0 to 9. And what we want to do is we have a kitty picture. Our key is the picture of the kitty. Wait, it's up here. This kitty picture up there. And that kitty picture is going to be our key for finding the kitty. All we need is our magical hash function, which is our total kitten score. That's what we use. All right? So here we have this first picture of kitties. And we're going to try to find these kitties. All right? And this is really important that you do not need to memorize the kitty scoring, the kitty hash scoring. So let's look back. So these features come from the kitties, right? So we get +2 for each kitty sitting or standing. So we got 2 sitting kitties there, I think. So that's a 4, a total +4. There's no orangeness. We have some blackness in the kitty fur, so that gives us 1 and 1. And we have some grayness. We do, because they're gray tabbies. Then +1 for fluffy kitties. These are fluffy kitties. Do not argue with me that these are not fluffy kitties. These are fluffy kitties. These are both tabby kitties. Nobody is in mid-mew. Nobody's laying down, and nobody's in a costume. Okay? So if we add up all these numbers, we get a total kitten score of 16. Where are the street kitties? These kitties are kind of bougie. Look, guys, you know, we have a home for all kinds of kitties. Don't start accusing my kitties of being like bourgeoisie kitties. Okay. Now, so our total kitten score is 16 over here. Total kitten score is 16. Define tabby. Tabbies are the sort of kitties that are like tiger striped. That's a tabby kitty. So you can have orange tabbies or gray tabbies. Yeah. Okay. So if our total kitten score is 16, where should I look for this tabby? Right? I have 10 array slots, and the TKS is 16. So where am I looking? We should all get kitties. Anybody? We gotta find these kitties. 6. Yeah, let's look in 6. Let's look. Oh, guys, it's those kitties. We found them. So good. So good. We found our kitties. Okay, so I'm gonna leave this sort of like we've already found our kitties here, but we're gonna put them back. Right? They're safe there. We'll put them back. I love when I do this in class, I hand these out to everyone and I say who has 6, and then they'll open they're usually in an envelope, and they'll open it. And I swear to you, every time I do this, the first time I do it, students clap. They applaud. They'll be like, oh my gosh, it was there. Like it was a magic trick. It's not a magic trick. I put it in 6. Anyway, awesome. All right, so next kitties. All right, next kitties. Oh, yeah. So these kitties, I can't wait to hear what Jeremy has to say about these kitties. These kitties are pretty bougie. I mean, look at them in their fluffy little quilts, and they're so sleepy. All right. So none of them are sitting or standing. None of them are orange. All right, we got 2 oranges and a gray. So the gray one is a gray tabby, so it's got some black in its fur. It's got some gray in its fur. We've got all 3 of them are tabbies. So to answer the question, these are 3 tabbies because they're kind of got that tiger stripe situation going on. These are good kitties. All right, Jeremy is a fan of these kitties. All right, good. See, if I didn't have to prearrange this, I would add to the total kitty score for future semesters a Jeremy Van Grack's 5-star rating of each kitty picture. Those kitties are offensively privileged. Oh, no. They didn't mean none. Okay, so their total kitten score is 14. So where are they? Where are these kitties? Where are these kitties, guys? That wasn't me. These kitties are offensively privileged. See, yeah, so am I. I have that in common. 4. We got 4. Yes. Here we go. Let's see. Kitties in a blanket. Yeah. Awesome. They're in 4. Cool. All right. Here we go. We got a new set of kitty. So this guy's kind of a romper. He's romping, I think. Don't you think he's romping? He looks like he's up to stuff. So, okay. So we got this romping kitty. And he's got some folded ears. This is a Scottish fold. They're awesome. I have Scottish folds and Manxes have very similar. They're like close together genetically, and I always have Manx cats, and I love Manx cats because they're kind of like puppies. They're like puppy dog hybrids. Okay, he's a 10. Oh, okay. Yeah, I need to rework this, and then future semesters I'll be teaching this class like 10 years from now. They'll be like, who is Jeremy Van Grack, and why does his opinion about these kitties matter? And then they'll get a lesson. This man gets into trouble. He's got character. I couldn't agree more. He's romping. He's getting into stuff. He's laying down the law. Okay. His TKS is 8. So we don't have to do much math to know that our rompy buddy is here. There he is, getting into trouble. Our rompy buddy. So much character. He's a good guy. All right. So now we're gonna go to the next one. Oh, look at these guys. I don't think Jeremy's gonna have a high opinion. I have to wait on each one to get the Jeremy opinion on these kitties. Okay, there it is. It's on the stream now. What do we got? Who do we have here? This is a mischievous kitten, all right. They all. Okay. So here's their total kitten score. We'll just have to take it for granted that I actually did go in and evaluate all of these kitties. None of them have been in a costume yet. So, all right. So we're at 16. So where are we gonna look for these kitties? Let's see. Where are they at? I get 6. Oh, okay. Let's look at 6. Wait, we remember these kitties. These are the bougiest kitties, if I recall. If I have the Jeremy rating system correctly, these are the original. So how are they at 6 though? What? Okay, so let's be engineers, right? Let's be engineers. Where would we put, if I go and I find 6 already has kitties in it, right? So whoever went and put these kitties in, they tried to put them in at 6, and there were other kitties already there. So where would they go next? Can't reuse keys. Can't do it. Well, let's just go next door. So we knocked. Ooh, that even worked because it's wood. We knocked. I'm glad my dog didn't freak out. Who am I kidding? He's sleeping. So we knocked. there were already kitties here. So let's go next door and see if there was a spot for those kitties there. There's our kitties. So 7. So sometimes you will hash your key, and the value that comes out when you mod it against the array size will give you something that's already in the array, right? And so what this is called is a hash collision, right? 2 kitties tried to go into the same spot, and they both can't be in the same spot. So we resolve the hash collision by, and next time we're going to talk about a whole bunch of collision handling techniques. But the one we're using today is, and forgive me, this is the name for it. I didn't come up with this name. It's called linear probing. So if there's something already here, then you linearly look down the list to find the next empty spot. And so for a find, if you don't find what you're looking for when you initially look for your kitty, then you keep going until you find the kitty that you need. What if 7 is used already? What would happen then? Let's keep kitty hashing, guys. Oh, look at this guy. I like this one because this kitty looks simultaneously happy, but also kind of sassy. It's kind of got a sassiness to it. And this, Jeremy. And this kitty also, I think it's used for a lot of memes. Also, this kitty is mid-mew. So we're going to get some mid-mew points here. That's exciting. You guys are having a lot of questions about the probing. I've designed this exercise that will hopefully answer them. But if you don't get your question to your linear probing answered, hold on to them and I'll answer a bunch of them at the end. Seems like a pretty chill kitty. All right, I'm glad. We got the Jeremy verdict here. Okay, so it's a black and gray tabby. We get a +1 point for mid-mew. Yes! And the kitten's also laying down, so this is a pretty good one. By the way, the rompy kitty, he got a +1 for his folded ears. So we got a 7 here. Oh, no. Wait, so, we went to 6, and then we have our other cat in 7. This cat actually doesn't even have a thing that hashes to 7. It just happened to not belong in 6. Well, now we're looking for the thing that actually should belong in 7. So let's go. We know that 7 is these guys, right? So we didn't find them. So we looked at 7. Now we'll look at 8. Oh, it's our buddy. It's our rompy buddy. All right, okay. So then let's go look at 9, right? Ta-da! There he is. There he is. Found him. Got him. All right, so we had to go a few hops to find our buddy. Now, you might be thinking, isn't this going to get slow eventually? Yeah, and we'll deal with that next time. So 9. You guys got it. He was in 9. All right, here we go. Oh boy. Oh, look at these kitties. And here's why the costume one comes into effect. What do we think of these kitties? Oh, okay. These kitties are going to get a pretty huge score. Okay, let's see. I'm assuming there's a long opinion. They're funny AF. A the Fs. They're funny A the Fs. A to the Fs. I can't say that because this is on YouTube and I checked the "this is made for children" box. No, I didn't. This is not made for children. Alright, so they have a TKS of 11. And so we got 2 kitties in costume. So that was quite the score multiplier. Wait, did I even do this right? Well, anyway, we're going to have to operate under the TKS of 11 here. And the reason we give a ×2 is to pay our respects, to put Fs in chats for the people who died putting those kitties into those costumes. All right, so we're going to look for 1. Bam, there they are. There they are, and they're in 1. just as we expected. We didn't have to hop around, so we're still fast. Still constant time. They look really fly with the hats. They do look fly. They're ready for a night out on the town. Okay. So here we go. Oh my gosh. It's a complete buffet of cuteness. Look at all this cuteness. Oh my gosh. That's so much cuteness. Yeah, let's get an F for the kitty costumers. Thank you. Yeah. They need to be. It's a thankless job being lacerated to death. So which one? What do we think? This is a lot of kitties. They all have very good posture. Like, I'm a little unnerved by their posture. Like, how they must have had some sort of feathery thing. So this is a massive kitty score. Look at that kitty score, 33. It's just because there's so many kitties. It's not because they're good kitties or bad kitties. So where are we gonna look? Well, we're gonna look in 3. And what do we have there? Oh, we have them again. So at this point, we're just showing that, like, we're going right to the spot where our data is. We don't have to search anywhere. We're still quite fast. Okay. Oh, look at this guy. Look at her. Look at her. Oh, she's so cute. She's ready to get into some trouble. Get into a particular kind of trouble. Oh, that's so good. All right. So what do we got? We did not count this as a fluffy kitty. I could see there being a debate. I think this is a floofy kitty. All right. So, we have a TKS of 7 on this one. Woo! 7. No Dr. Pepper today. No, we drink whatever fake sugar thing is actually still at the grocery store. That's the rule. All right. So we have a 7. So we get 0. Ooh, you guys are fancy. So we look at 7, and we're just because we need to look at kitties. Remember these guys? So cute. All right, what about these guys? Ooh, here's our real buddy. Here's the romper. She's gonna do big things. She's gonna be quite the cat. Oh, we have 9. So now, we've hit the end of our array. Oh no. So, what we have to do is we have to take a trip back to the front of the array, over here at spot 0, and here we have her. Here she is, and she's gone all over town, right? She's fancy. She's been knocking on doors. She's super fancy. 8 is the best one, not gonna lie. I will agree to disagree. Well, you haven't seen them all. Okay, so now here's a kitty. This is one of the best kitties. Tie for best kitty. This kitty has not had a home found for it yet. This is my kitty. This is Tybalt. This is Tybalt when he was probably like 12 weeks old. Baby Tybalt. His head was perfectly round. It's not perfectly round anymore, but it was when he was a bebe. So now we've been doing retrieves. All of these have been finds. We have a kitty, and then we want to find the kitty in our hash table, right? And so if we go to a spot and we don't get the kitty that we're looking for, we linearly probe and loop around to find our kitty. So now we're going to do an insertion, and we have to find a home for Tybalt. So, fun fact about Tybalt. So Tybalt is a character in Shakespeare that Romeo kills in Romeo and Juliet. However, that was because Tybalt killed Mercutio. So that's not fun. But Tybalt is also, from French folklore, a character who is the Prince of Cats. Huh? How big of a nerd am I to research my cat names that much? The answer is huge, huge, huge nerd. Alright, so we have Tybalt. He is a fancy young lad. He has a TKS of 6, right? So what we're going to do when we try to insert our buddy Tybalt here is we're going to look and say, all right, well, is there a spot at 6? No! Plus 10 TKS for intelligence. What about at 7? No, there's already a kitty there. All right, what about at 8? Oh, that's our buddy. Tybalt would love to hang out with this guy. Actually, no, he'd probably be terrified of that guy. Jules would hang out with him. We have this guy. So we have to come all the way back around to 0. And we look at 0. Oh, we already have a kitty there. No, what about here? Oh no, here's our costumed kitties. All right, what about two? What about two? It's a placeholder pup. So this was empty. A placeholder pup is, these puppies are doing good service. They keep the spots warm and hospitable and up to date. They're like house sitters for array positions. And so this placeholder pup has been holding a spot for Tibble. So now Tibble can be at home with he will now Tibble will be in spot 2, and that's just great. So we found a home for Tibble. Wonderful. Bro, what drama. I know there were pups among us the whole time. What a plot twist. You got shalamaried. Shamamalama dinged. Yeah. Okay, one more kitty to hash. That's my boy Jules. Boom. Jules has helped me teach. This is baby Jules. He was still huge as a baby. He's very young in this picture, but still quite large. So we have our friend Jules. Let's see what his TKS is. His TKS is 3. So let's look. Oh no, that's where all our kitties are. Yeah, the pup and Tibble, they're buddies. They're hanging out. They're getting along. Oh no. Okay, so 3. And then finally we get to 5. And there's a pupper there. Yay! So, Tibble and this pupper are going to be best buds and hang out in array position 5. Now, those of you keeping score on how many kitties are in this array is now completely filled with kitties. So what happens when our arrays fill up with stuff in when we're doing array operations? What do we do when our arrays fill up? Kind of harsh on his own cat. Look, I told you the total kitten score is not a measure of quality. It's an addressing system. It's not a measure of quality. We resize. How much? We add 1 spot, 2 spots, 3 spots, 4 spots, 20 spots, 100 spots. How much? We resize by how much? We double it. So, we have 10 kitties here. And what we would do is now that we've filled our array with 10 kitties, we would double our array to have home for 20 kitties. But here's the thing. You guys said we copy it straight over. Is Jules, or is this one? So remember, this had a total kitty score of 33. What if I leave it at 3 and I go looking for it in a size 20 array, what index would I look for it? So suppose my array has been doubled and I know that these guys are a total kitty score of 33. Where would I go looking for them in the size 20 array? It'd be in 13. You guys got it, right? So we can't actually just copy the array over like we do for a normal array. Because then, when we go looking for our kitties with a kitten score of 33, we'll be looking in 13 where we had copied them over in 3. And Danielle, so on point, she actually used the correct term. What we do instead of copying them over into the larger array is we rehash them into the larger array. So what we do is we gather up all of our kitties again, and then we go through them and we say, all right, what's your total kitty score? We'll mod that by 20, and then we'll put you in the correct spot. So you basically repeat the whole process of looking at the total kitty scores and putting them into their correct spots. So whatever 33 mod 20 is, Jeremy, it's not hard to do 33 minus 20. So they would go into 13. So that's where you would initially look for them. You might get a hash collision and have to linear probe, but there might not be anything actually at 13. Okay, so that's kitty hashing. And we're going to talk a little bit more. Is this the catch for hash tables? No. The catch for hash tables, the spoiler alert spoiler, is if I wanted to get all the kitties out in their sorted by total kitty score, a hash table is terrible. The hash tables deliberately try to mix up the key values. And so the catch for hash tables is if you care about the sorted order of keys, you shouldn't use a hash table because you'll get really bad performance. Yeah, it's 13 because 33 mod 20 is 13. So whenever you get your hash, whenever you put your hash function in, so total kitty score is our hash function, you'll get a number based on the key. The keys here were the kitties, the pictures of the kitties. We hashed the pictures of the kitties to get an integer value, because hash functions give you integer values. And then we take that integer value and we mod it by the size of the array. And that gives us where in the array to first attempt to either insert or find the thing that we're looking for. You're not dumb, Teddy. You're not dumb. Good stuff. All right. So let's do a bit more slideroos. I'm going to go back to standard configuration here for presenting. Well, you guys have questions. If anybody has any lingering hash table questions about what we talked about or how we found homes for the kitties, pop it in the chat. I got sands to print out. What? I'm so lost. Okay. All right. Oh, we just went over the function. All right, so we inserted kitties. I just want to show you guys this GIF of kitties being inserted into a box. So just imagine that's how they all go into their home. Oh yeah, how do we remove a kitty? So suppose we find we want to rehome our kitties someplace else. What do we do? So I'm gonna let's go back to kitty lookings at. Okay, so I have my wait, how did this get so wretchedly out of order? I shuffled them by accident. So we have 0. Really? Wow, I did like hashing of my own. So 0, 1, 2, 3, 4, 5, 6, so on and so forth here, right? Let's just make the hash table of 4 elements. Or no, sorry. I'm missing 3! What a mess! It's because they're all tri-folded. As a paper folder, tri-folding annoys me because you need more reference points than actual creases, final creases. Anyway, so we have 5 things, and they've all been hashed in here. If I want to remove the thing that's at 2, how do I do that? Do I just put a placeholder pup there? Or actually, let's say, wait, who has the placeholder pup? Yeah, so if I want to take Tybalt out for some like snuggle times, right? Can I just put a placeholder pup there? They're just some value. Like what do we do with this spot? So what did a placeholder pup meant, hey, you can insert here. Or if you're doing a find and you hit a placeholder pup, that means you haven't found the thing that you're looking for, right? So the thing is, we can't use a place. So the question here is, can we use a placeholder pup after we remove something? And no, we have to use something else. We have to use something that it's some sort of sentinel value that means that something is here and it was deleted. Because if say I put something here in spot 1, and then I tried to put it in spot 1, but I couldn't find a spot, and suppose Tybalt was still in spot 2, it would look here and be like, Tybalt's there, and put it in spot 3. If I remove Tybalt and put a placeholder back here, and I try to look for this thing at 3, I'll look for it first here, because that's where it originally hashed. Then I'll look and I'll see a placeholder pup, so I'll be like, oh, I guess this kitty is missing, right? When really, it is still here, it's just you hit a deleted spot. So what you need to have, you need to actually, when you delete something from a hash table, you need to make special notes so that when the linear probing comes through and it hits this, it hits this element of the list, it knows that it has to keep linear probing. Because if it's a place that's never been inserted to, then if it hits that, it'll be like, oh, I'm done, there's nothing here. But if I come back, but if I delete something from here, I need to have something that tells the linear probing to continue. Does that technically implicitly offer some security, like since the values are randomized? Technically, I mean, if somebody's like editing your memory directly, like if you get down to the array level of your data structure, something horrible has happened. Probably. It's kind of one of those security things of like, is this really, like, it's sort of like putting a bomb in the middle of your cache of diamonds and be like, haha, if they steal my diamonds, they'll blow up. And it's like, yeah, but they've already gotten your diamonds. So, usually you would want it. Yeah, technically, hashes are used for security, 100%. So if you've heard hashing before and your brain is going to security, that's a totally natural thing because it turns out functions that are good to use, like good kitten scoring functions, but good hash functions, do a really good job scrambling everything up so that you don't get these you don't have to do this linear probing. So if you have a really good hash function, then your hash table is going to be really efficient. But also, if you have a really good hash function, you have a good way of taking data and scrambling it in some way, which is good for security. So you want a placeholder kitty, or maybe like a placeholder ferret? What do people call those? Like tube puppers? Like, I don't know, something like that. Okay, let's go back to Chrome. Chrome. All right, we have a few minutes, so I'm just gonna talk a little bit about collision management. Yeah, so this is a really relevant title slide, and I apologize for that. It's just it's a little too relevant. We didn't do a Would You Rather. Actually, we didn't do a Would You Rather because we did... didn't we already do a dump thing? I feel like I've doubled up on the dump question. Oh, okay. Tenny's asking a good question. So rather than move on, we're going to answer Tenny's question. I'd much rather do that if there's questions. But the first one, the walking, yeah, I think we did that whole question. So that's a recycled one. All right, let's go over this again because this is a fairly important point. Okay, actually, I should have just gone. It's weird because it's not a mirror image. It's like this is my left hand, which is appearing on my right, which is weird. Okay. So, say I go to insert these kitties, okay? I go to insert these kitties, and I find they have a total kitty score of 1, right? And so I go in and I insert, and I look in 1, and I see that there's already kitties there. And I go and I look in 2, and then I lost Tybalt. Well, if I went into 2 and I saw a placeholder pup, I would be able to insert the kitty there. But I can't because Tybalt's there, right? So I have to keep probing. So I remember these kitties wanted to go in the 1 spot. These kitties wanted to go in the 1 spot. Couldn't go there, so they went here, and now they're going to have to be stuck in the 3 spot. Okay? So now let's do a find for those kitties. So we know that they would hash to 1. So when we go and look in 1, we see, oh, there's a kitty in 1. We go here and we see, oh, Tybalt's in there. So then we go to 3, and then we go, oh, I found my kitties, even though they hashed to 1. The problem is, if I take Tybalt out, and I don't do anything special, and I just put a placeholder pup here, if I go to look for the kitties again, I know they hash to 1, and I'll go and I'll look in there, and I'll be like, is this the kitties in the cups? No, it's the awesome kitties in the outfits. Are the kitties, are they in here? And then we get a placeholder pup. And so the placeholder pup means nothing's ever been inserted here. So if I saw that when looking for the kitties that eventually made it to 3, I would think, oh, they're not in here. They're not here. When actually they are, they're right here. So what I need is I need a special value, like, I don't know, it's maybe like a placeholder pup, but it's got some like incognito mustache. Like that. So it's not quite a placeholder pup. And what this kind of placeholder pup means is that it's like a dirty bit. So that's why it's got like this skeezy mustache. So that means if I see the mustached pupper, that means, okay, well, your thing's not in this spot, but you should keep looking because there was something here and it's gone now. Does that help? The delay got longer. And then it looks like it skipped over where I said, did that help? So the hash function is, okay, Colin's making an awesome point. So let's talk about performance, right? Our total kitten score computation we'll assume is constant time, which gives us an index into an array, which if there's no collisions, we just go boom right into that array, and we either do our insertion or our retrieval directly into that array. Nice. That's constant time. I don't have to look at any place but 1 spot in the array. Now, what if the array's starting to get really full? What if I have to do a lot of linear probing? What's my worst case on linear probing if there's only 1 spot left in the array? What's my worst case? So my array, I have 9 kitties in my 10 slot array. What is the worst, and say the open spot, the remaining open spot is 3. What is the worst case hash value to get, and what does that cause the performance of that insert to be? So the open spot is 3, and there's 10 spots. What is the worst case index to have to be looking for, and for an insertion, and then what time performance does that give you? There's okay. To answer your question, Tenny, there's nothing bad about you can replace the placeholder pup with the mustache, but if you're doing a find and you see the placeholder pup with the mustache, you should keep linear probing. If you see a placeholder pup without a mustache when you're doing a find, you should stop linear probing because that is a genuinely open spot that nothing has ever been inserted to. So 4. So go back to the other question. If this is the open spot and the things and the list is it's the only open spot, the worst place to look is 4, because 4 will have to look at 5, 6, 7, 8, 9, 8, 9, 0, 1, 2 to find 3. And so in result, it's looked over the whole array to find this open spot. So how do we combat that? Is linear time, and we want constant time. So what can we do to keep our to keep that from happening? So what caused that to happen in the first place? Because it doesn't matter how good your hash function is, you might just get unlucky and get a 4, which would be a bad worst case. So the answer is not improve your... You could have the best hash function. You could have like a perfect hash function. Well, no, you couldn't have a perfect hash function. You could have a very, very good hash function. There is something called perfect hashing, and it actually gets around this problem more directly. But the way that you solve this problem is you just make sure that your array doesn't have a lot of stuff in it at any given time. And that's what's called a loading factor. So, thank you, neighborhood children. I don't know if you heard the child screaming. There it goes again. Your loading factor is the number of things in your array over the size of your array. So if I have 3 kitties in a size 10 array, my loading factor is 30. So what you can do is, instead of doubling the size of your array when you get full, you double the size of the array when your loading factor gets unacceptably high, which I believe experimentally 30% is a pretty good loading factor. So what you do is, if I have a size 10 array and I get 3 kitties in it, that's when I double it to size 20, not when I fill it all the way up with kitties. And so what you do is you keep a lot of space. You keep a lot of placeholder pups around so that you don't have to do a lot of statistically have to do very little linear probing. So that's one way to help, and then another way is to have a really good hash function. Another thing to do is to just let kitties live together. Just let kitties live together. So when you have a hash, there's another thing called separate chaining, where instead of doing linear probing, you just let kitties live. If 2 cats hash to the same spot, you just put, and I know this is going to upset you, you put a linked list there of kitties, and then you just let them all live in the same spot. And then, again, you'll still have problems where if all of your kitties are in the same spot, then you have to go potentially down. But you just, again, with the loading factor, just manage your loading factor. Do we ever decrease the size? Absolutely. We don't want more memory than we need hanging around. So we can decrease the size when our loading factor gets below a certain value. So if we've removed a lot of stuff from the hash table, say our loading factor has gotten down to like 5%, so only 5% of the array has stuff in it, then we would halve the size of the array, and then that would bump it back up to a loading factor of 10. So a high loading factor means you're going to have more hash collisions. A low loading factor means you're wasting a ton of memory because you're holding on to a giant array for a small amount of kitties. They don't need all that space. And the actual implementation of hash tables isn't that bad. They're about as bad as dynamic arrays. They're kind of another flavor of dynamic arrays that are blazingly fast. But they don't maintain order. They do not maintain order. They don't even keep the order that you inserted the things in. Like, anything with about order is out the window with hash tables. So they don't, unlike queues, they don't know about the order things were put in. They don't. And like lists, there's no way of ordering keys. So if you need things in any kind of order, a hash table alone will not do you any favors. In Python, you can make what's called an ordered dictionary, and an ordered dictionary will it will let you do a key value store in constant time, and then if you ever want to get the keys back in the order they went in, it will give you that, and all that's implemented under the hood is a hash table with a linked list, like right next to it. It's just both of the things there. So if you want the list of keys in the order they went in, it just gives you basically the linked list out. And if you want to do key value operations, it lets you alter the hash table. And yeah, but hash tables are implemented everywhere. Like I said, caching. So what you do, an example of a hash table being used for caching is you have a website, like a URL you want to go to, and your computer might have it cached, like the contents of that website cached. So what it'll do is it'll say, it'll go to the cache and say, my key is the URL for this website, and the cache will say, oh, okay, that's in here. Here's the contents of the website. So that's how caching works. Now, there's a lot more sophistication going on in validating caches and things like that with using timestamps and stuff. But ultimately, it's a hash table. Hash tables are used, like I said, for NoSQL stores, which are just basically giant hash tables. But yeah, they're really, 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 really efficient key value stores because everything's in constant time. And what I'll tell you is all these things that might make it not constant time, people have come up with little tweakly hacks that make its theoretical over amortized performance back down to constant time. Even having to double the size of the array is actually constant time when you look at overall operations. So, any other questions? All right, so that's day one of hash tables. Tomorrow, oh my gosh, it's Wednesday. Oh my gosh, the week is having progress. It's Wednesday, so on Monday we're gonna go over those hacks. Also now, I wrote a thing last night that lets you see the office hours queue in all its glory. There are 25 of you in there right now. Hopefully this will cut it down on spam. The numbers you see here are your integer Discord IDs, and there's instructions at the top of this webpage for how to find out what your ID is. Did not want to post your personal information on the public internet. This is the public internet, so if you really don't want someone to know your identity, then dissociate your name from your actual Discord account. Your nickname in our channel will always be your username, but yeah. Oh, you were like 10 minutes behind. Oh my gosh. That's unfortunate. So this is up. I'm continuing to work on the Discord bot to try to make office hours better for you guys. 25 students in an office hours queue is not ideal. Our TAs are very tired and they're doing their best to help you guys out. It's a difficult project. To quote Dr. Dixon, I've sort of assumed, he said something and I've sort of taken it on as my mantra in these times, as everything sucks. So this sucks. Online classes suck. Not being able to hang out with your friends sucks. Not being able to play our board game sucks. Everything sucks and it's bad. And we're trying to figure stuff out as we go, and we really, really appreciate your patience with this stuff. 341 is a very challenging class, and so it's really, really hard to run it online. But getting through these projects makes you a better programmer. They're interview questions, essentially. Like, any of the stuff that we're giving you, you could easily get in an interview questions. These are not just exercises to make your life difficult. Well, they are, but you will actually use their exercises interviewers use to make your life difficult. And so we're giving you practice in a friendly environment on having to work through these problems so that you get really comfortable with them. So, do I have power to confer a PhD on Tybalt? Dr. Tybalt does have a nice ring to it. I agree. Yeah, I don't know. I don't think he's real dumb. He's real dumb. So, hopefully this queue. And, yeah. And so occasionally, also, if you don't see the queue moving, it's because we're between office hour sessions for TAs. And for 341, they're leaving the queue open so that you don't lose your place in line when somebody goes off duty. So on the course website, you can see the TA office hours. So this might not always be 100% up to date. Some TAs have been getting sick and things like that. But as you can see, like on Mondays over here, there's a big gap of a few hours and so on and so forth. So there's only one TA on duty this time, and it's really hard with the communication problems for a TA to get through to help a student in less than 20 or 30 minutes. So we have like 12 hours of office hours back up here. So I'm glad you guys are using this resource, but it's a bit saturated at the moment. Is that possible for cats? I don't know. I feel like he'd be a better... no, maybe PhD is good for him. That way he can be quiet. He'd be a quiet researcher. Jules would have to be a politician or maybe a military figure, because he's very, like... He kind of runs our house. Like, he made Natalie stop working yesterday. It was like, it's time for you to be done. It's 5:30. I'm going to sit on your lap and purr really hard until you give up. So yeah. All right. I'm going to go over one thing on the project before we... Look, it's Fibonacci stuff for 201. Again. There's a point that a few of you have asked me about, and it's causing some confusion, and it caused me a bit of confusion as well. I know that you can't see anything. I'm working on it. OBS doesn't remember my... Okay. When is the next test? April 22nd is the next test. That is the current... Oh, do I have this upside down? Yes, I do. All right. So, you have comma-separated files. So, CSVs, essentially, for scanner. Not scanner. You have weights .txt, and you also have scrambled. This isn't working very well today. .txt, and they're CSVs, so they are essentially two-dimensional arrays. They're both waffles, and you're trying to produce an output array, 2D array, waffly 2D array, that is the unscrambled thing. And so weights. So if here we have the value 38. And this is 1, 2, 3, 4, 5, 6, 7 wide, right? So if this is 7 wide, then what that means is the first value in weights and the first value in scrambled describe the 38th thing in this array down here. So if I go 1, 2, 3, 4, 5, 6, 7, whoop, 8, 9, 10, 11, 12, 13, 14, 15, 16, all the way down to what's 38 mod 7. 38 mod 7 is 3, so it'll be it'll be row 5, column 3. So 38 actually maps to row 5, column 3. And so that means that the first value in scrambled is describing what color you paint row 5, column 3. And the way that you got row 5, column 3 is by the fact that that's what was the first element in weights. (22nd) is the currently scheduled exam 2. And it'll be take home. And depending on what I write for the exam, you will get 24 or 48 hours to complete it. If I think the exam will take you 2 hours, I'll give you a day, and if I think it'll take you 3 or 4 hours, I'll give you 2 days. Also, just life tip. When you're budgeting time for other people, use that kind of scale. Like if something's going to take an hour or two, give them a day. Because it doesn't take 24 hours to take the exam, but in a 24-hour window, it's hard to slot in an hour or two, right? Like that's hard to do between eating and doing all the other things you do in your life. So if I give you 48 hours, I do not expect it to take 48 hours. I expect it to take 2 to 4 hours. Is the load file supposed to load in the files or insert into the tree? Yes. It loads in the file and does the inserting. Isn't that what the project description says? Yeah, load the data files and insert data into the data structure. So I know what ends up happening is you read the data structure and then you look at the H files and you look at the comments in the H files. But a lot of times if you check the project description, it'll answer a good amount of your questions. Certainly not all of them. But in terms of what you're expected to do, most of the information should be there. So, okay. And so, yeah. And you already know the range of values that are going to be in weights. You already know the range of values that are going to be in here because you know the height and width of the image. And so the range of values in weights will be 1 to height times width. And so you can divide this range into height many nodes, S nodes. All right, I'm going to go back to the YouTube thing because I think my question gathering apparatus has fallen asleep. No, okay. Is the stream frozen? No, because I see what I just wrote. Any other questions? You guys are also released into the world. I'm done. I'm just taking questions now. So if you have some place to be, go be there. There is about a 10-second delay on the stream right now, maybe 15. All right. Difficult project. Yeah. Be patient with the help resources. It's a difficult time. I know everybody's running out of patience. It's tricky. Question about BST. Hit me. How often should we be rebalancing? Okay. You rebalance, you rebalance your BST. So, say I have some BST here. My computer is chugging for some reason. I wonder if I still have my local web host running or whatever. So say I'm inserting a new value. Let's change our color over here to like, ooh, pink. All right, say I'm inserting this new node, right? It's gonna go here, and then it might 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 go here, and then it's gonna go here. That's gonna be our new node, right? After you insert the node, then you're gonna look top to bottom. You can actually do this on your way down sometimes. Not really, you have to kind of go back over. After you do the insert, and if you've done it differently, but it still like works and you're getting the same results, don't freak out now. Keep on what you're doing. But if you're still wondering about this, you're gonna go to this point, and then you're gonna call your imbalance function. And you're gonna call it on this node. And if it returns true, you rebalance. If it doesn't, then you go down here and then you ask, is this one imbalanced? And if it returns true, then you rebalance and you keep going down. As soon as you hit something that needs to be rebalanced, you rebalance it and then you're done. So if this one, if the root, because maybe that's the case. Maybe finally there's a height differential between these two subtrees, that the root has become imbalanced. Then you shove everything in an array, pull it back. That's the new root. You're done, right? So the thing that is determining how much rebalancing you do is the imbalance function, which is a parameter to your BST class. So it's actually the user of your binary search tree that determines how aggressively your tree is rebalanced. When we load in the files, do we load in the characters and weights as a pair? Yep, absolument. You should be rebalancing after every insert that has imbalanced return true. You could write imbalanced. You could write an imbalance function that says return true, which would mean that your tree rebalances after every single insert. But usually it will check the heights and the sizes it's given and decide whether or not that particular subtree needs rebalancing. Got it. Cool. All right, guys. I'm going to go out and keep doing teacher stuff. If I have the spare time, I will pop in and help out with office hours. So you might get stuck with me in office hours. Yeah, oh yeah, if you rebalance after every insert, you have linear performance because the insert is linear time. Yeah, so it's a nightmare for runtime. Okay. All right, guys. As always, it's been a delight. Thank you for joining me for kitten hashing. Yeah, try to keep things lighthearted and enjoyable as much as possible. Next time we're going to talk about hacking, doing some hacks, some hash table hacks to get some more performance, squeeze some more performance out of that. So yeah, all right. Hopefully the delay was more manageable today in terms of stream delay. I hope that feature helped out. Good luck on your project. Get your BST working. Get it well tested. It's worth the majority of the points. Do not just finish the BST and then immediately start on the scanner. Make sure that you have a good test suite. You're being graded on the test that you send in. If you just send us the test that we gave you, you will lose credit. You are supposed to write your own test cases that test for things. And there is a testing seminar that has been sent out. If you don't have a link to that, ask for it in Discord, and someone will give you a link to the, you can ping the TAs, and someone will give you a link to the seminar the TAs gave on writing tests. But make sure you do that. Do not just charge into this whole scanner splice tree thing if you do not have your binary search tree stuff sorted out, okay? Also, if you haven't gotten them, the grade sheets for Project 1 are coming out. What you see in Blackboard is your final scaled score. Explanations for that scaled score will be coming out soon. Hopefully, I believe it's this week. They exist. I think Dr. Marin is just waiting for all the professors to explain the scoring before the grade sheets are returned. If you have a question about what you see in your grade sheet or just grading in general, you can email me, but what I'm going to tell you to do is to open a office hours session next week after this project is due. Open an office hours session and then talk to the TA there, and then the TA will look into it. It won't necessarily be the TA that graded your assignment, but that TA will be empowered to look at your grading and maybe make some revisions if they're appropriate, or explain to you what happened when your tests were run and so on and so forth. But don't even get into the queue. I've given the TAs the ability to reject people from the queue, so if they see you in the queue with questions about your Project 1 grading, you will get popped off the queue and asked to wait till next week for such questions. Yes, it's in the Discord. If you're somehow getting to these videos and you're not in the Discord already, get in the Discord. Everyone should have gotten an email. I have evidence in my inbox that you all got emails. So you all got emails about the Discord a while back. So if you're having trouble with the Discord, please do reach out. That's where a lot of the resources for this class are being put right now. And it's also where you get help, presumably. Okay. All right, guys. Have a good weekend. It'll be a much better weekend after Friday, I'm sure. But keep calm and carry on. Bye.